All right, the representing functions worksheet. Let's go ahead and work through that. Let's see, first review problem, write the simplest polynomial with roots of 3, -5, and 1. That would look like x minus 3, x minus -5, or x plus 5, and x minus 1. It didn't specify what form it wanted it in, so we can leave it in a factored form. If we wanted a standard form, we could multiply those together. But that's sufficient for what it asked for. Solve this system. So it looks like maybe if I took this top equation, I multiplied everything there by 3. I'll do an elimination method. Give me a 9x minus 6y equals 12. And keep the bottom equation as a 2x plus 6y equals -34. If I added those together, I would get 11x is equal to, looks like -22. So x is -2. And I took that second equation, 2 times -2 plus 6y is equal to -34. Get the 6y is -30, and so the y is -5, and so the solution of the system is -2, -5. All right, Abram leaves his house and walks to the bus stop. After a few minutes, the bus picks him up and takes him to the park where he plays basketball for a couple of hours before his mom picks him up and takes him back home. Sketch a graph of Abram's distance from his house and explain your choices. Okay, so let's put a time axis in here somewhere, and this will represent then the distance from his house on the y-axis. The thing that we know is that over the course of the day, he started at his house, and we know that he's going to be back at his house again at some point later in the day. We don't know exactly how far the basketball court is from his house, but he's going to be there for a couple hours, and so maybe we'll mark this as that maximum distance. It will come up to here somewhere, and middle of the day for a couple of hours. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 or 13 hours here. We'll make it a 12-hour day. Okay. And somewhere in the middle of that, he is playing basketball for a couple of hours. We'll say he's that far from his house. We won't count the back and forth down the court as different distances from his house. Leaves his house, walks to the bus stop, so he's kind of walking this direction in the bus, or he has to wait for a little bit for the bus to get there, and then the bus gets there and takes him all the way to the park. So we'll do that. Our time is maybe not exactly on here, but we didn't mark it and say what it was. But there we've got a walking speed, waiting for the bus, riding the bus to the park. Then he is at the park for a little while, playing basketball. Then his mom picks him up and takes him back home, so there's not wait time anywhere. Mom just gets him back home, and then he's back home again after that. So that might be a reasonable choice there. We have the slow walk at the beginning. And then the bus is faster after waiting. And then straight home with mom. Okay, so there's some of the choices that we made along the way there. the bus maybe path was a little more jagged. It probably had to make some stops along the way, so that would be a good thing to put in there. It went for a little while, had to stop and pick up other people, went for a little while, had to stop. Okay, maybe didn't have to make too many stops along the way, but throwing those in there wouldn't be a bad idea either. Okay. All right, this is a cross-section of Marigold's swimming pool. She probably runs 3 hoses from her house to the pool that provide a steady flow of water. And we're supposed to sketch a graph of the water level in her pool as time starts, as time passes. So right now, this bottom part of the pool is not very wide, so it is going to fill a little bit more quickly as we go, or fill up fairly quickly, but then it's getting wider and wider, so the rate that it fills up is going to be slowing down. Might be, again, we don't have any axis on this necessarily, or any labels on our axis, so maybe it comes up to about this level and then suddenly gets really wide. So it feels like it should probably curve somewhat in this early part. Doesn't show that there very much, but then after that it's going to fill at a steady rate that is slower than what it was before because of how wide the thing is. Okay. So that has kind of the feel to it, to me. Okay. All right, when Stanley plants 100 apple trees on an acre of land, he harvests 5 bins of fruit per tree. For every additional tree that he plants on the acre, the yield drops by 0.1 bins per tree. Okay. So write an equation for the number of bins of apples he will harvest if he plants X more trees. So it is, as it is right now, he's planting 100 trees per acre and gets 5 bins of fruit per tree. So that sounds like 500 bins of apples per acre. But he is going to plant additional trees. So if we let X, let's define our variable here. X will be the number of additional trees per acre that he plants. Okay, so he's going to crowd some more in there. The yield drops by 0.1 bins per tree. So we have this 100 plus X is the number of trees that are on the new acre, and that 5 bins per acre is going to drop by 0.1 for every extra tree that he plants. So the 100 plus X is in trees. This is bins per tree, and when we do trees times bins per tree, the tree units will cancel and will tell us how many bins of apples come off of there. So we'll give this a name. We'll call this A of X, number of apples that he gets out of there. So how many trees per acre should he plant if he wants to maximize the number of apples from each acre? Okay. So assuming this pattern of how many bins he gets off of each tree, if we want to maximize the bins of apples from each acre, probably should he plant? Well, should be fixed on your version by the time you see it. Well, here's the equation. We want it to be maximized. So it looks like it's going to be quadratic. If we simplify this, the A of X is 100 times 5. There's a 500 plus a 5x minus a 10x minus 0.1x squared. That is a 500 minus 5x minus 0.1x squared. And if we want the maximum on that, this is a parabola that opens down. We were able to find maximums on that. You can plot this in the calculator if you want and find it, but if you remember, it's going to happen when x is equal to the opposite of b over 2a. So in this case, that is positive 5 over negative, or 2 times 0.1, so negative 0.2, and 5 divided by negative 0.2 is negative 25. And so it says what he should actually do is only plant 75 trees per acre. Okay, 100 plus x, but our x came out to be negative. So 100 plus negative 25, his best solution is 75 trees per acre. Should be able to verify that with a graph if you were to look at that as well. All right, let's see. Timmy's been keeping track of the number of custom knit beanies that she sells depending on the price that she puts on them. The information is in the given table. Find an equation to predict the number that you will sell based on the price.